Okay, we're going to begin by talking about some string algorithms. And in particular, we are going to introduce the Knuth-Morris-Pratt algorithm today, Kmp, which is used for string matching. But before we get to string matching, I want to talk just a little bit about some of the built-in algorithms that are usually provided for you in a library. So for instance, in the string library in C++, it's built into Python, things like that. So normally there are these sort of built-in functions that let you store strings. They let you do a comparison, sort of a greater than or less than. They will let you pull out substrings, pulling out just a piece of a particular string. They'll let you do things like concatenate and append. Sometimes there are things that actually let you do, let you split a string into different parts. So Python, for instance, has the split command. There are a variety of things there. But one thing to realize about all of the built-in algorithms is they are not necessarily the most efficient. And sometimes there's some hidden complexity in there that you might not be aware of. So it's not unusual that if you have a command where you are taking a string and adding on a string, or maybe even just adding on a character, and when it does this, for instance, if you do A plus equals B, something like that, that what it will actually do is make an entire copy of A and then add B onto the end and then reassign the copy back to A. Okay, so if A is a big, long string, and then we want to just add on one character to it, it's first going to copy this entire string with the additional character, and then it's going to replace the original one with that. So it's very common for something like that to be done in these built-in libraries. And so something like this might be an order n operation where n is the size of A, and that can end up taking a lot of time if you do this operation over and over. So you have to be a little bit careful about hidden complexity in some of the built-in algorithms that languages or libraries provide for you. So just be aware of that. Be ready to watch out for it. So a lot of string commands are built in for you, but sort of the most efficient things that you want to use usually are not provided by standard libraries. And one of these that we're going to talk about today is what is called Substring Search. And so the idea here is that we have some string S that we want to find in text T. Okay, so T is going to be a very long sequence of text, and S is going to be some very relatively short string that we're wanting to find in there. And so normally we would say that this is size M and this is size N. And so one way of doing this is that we have our giant list of text here, and we have the string, and we start comparing at the first element, and we just compare element by element. And if we ever find one that doesn't match, then we shift over one and we start comparing at the next element. Compare and compare and compare, shift over, compare, 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 and keep doing that. Okay, so that's the sort of most basic way of doing things. And in the worst, and so we're going to end up checking it basically every n characters. And in the worst case, we would have to check m different values if every time we got almost to the end and then it failed. So in particular, this could be an order nm operation. That can take quite a while, potentially. Now, I will say that the types of things that you often run into in English text, in the type of text that you would have in a written document or something like that, this isn't really the worst thing, because chances are strings are not going to match after just a comparison or two. You usually don't have to do that many comparisons before something doesn't match, and you can move on to the next one. So it's typically nowhere close to order nm, because you're usually not doing anywhere close to m comparisons per comparison, and it's a whole lot closer in practice to order n. So that's not the worst case to handle in like realistic text. However, there are a lot of things where we apply string algorithms to things that are not just English text. And one of the most common, I'll say, common might not be the right word, but one of the most useful cases for this is if you look at strings of DNA codes. So this is one of the fundamental things that comes up in bioinformatics. You have a sequence of DNA bases and you want to analyze that sequence and you want to find whether some particular subsequence is in there. And that subsequence is basically a substring. So in a DNA sequence, you just have a big long string of A, C, G, and T, or the base types. So basically those 4 letters, and they go into some giant string. So you might have a string like this that's 1 million characters long or longer, and you're wanting to find whether there's some substring that appears in there. And this is the sort of thing, a substring might correspond to a particular protein, for instance. Okay, so maybe we've got COVID viruses and we want to find a particular protein that's specific to the COVID virus, and we want to see, is that somewhere in this genetic string? Well, that's basically substring search. And the thing about this is, since we've only got 4 characters that we're looking for in this string, since there's only 4 options, it's actually possible to do a whole lot of comparisons and get a lot of matches, especially in a big long string, without the whole thing matching. And so you do end up getting something a little bit closer to the order n times m than you would with a typical English text document. Okay, so just realize that even though I'm going to give examples here that are in English, the real power of this algorithm tends to come when you have a much more limited set of characters where you're more likely to have a lot of overlaps that occur along the way. All right, so the basic algorithm that we are going to introduce here is the Knuth, Knuth-Morris-Pratt algorithm. Which is often just referred to as Kmp. And the Kmp algorithm, the idea of it is that we are going to pre-process a string, and then we are going to use that pre-processing to perform our substring search more efficiently. So as far as pre-processing the string, what we want to do is we want to know how far do I, basically, as I'm doing this comparison and comparing a string versus something else, how far do I actually need to reset once I find something that doesn't match? So let me give you a very short example. Let's say that we have a string A, B, B, A, C. Okay. Actually, let me change it. A, B, C, D. Okay. So there's my string A, B, B, A, B, C, D. And let's say that we come along and we have some text that we are comparing this to, and the text says is something like A, B, B, A, B, B, A. Okay, so notice these are not the same things, and assume this keeps going on. But when I do my comparison, I check the A and I say, yes, those match, B's match, great. Another B matches, another A matches, hey, we're doing well. This B matches, and oh no, we don't match there. So we do not actually have that string of text, if this is S and this is T. We don't actually have S appearing in T. At least at this point, lining up at that first thing. And so the next thing we could do is we could shift S over by 1. So we could say, okay, well, let's start checking here, A, B, B, A. And of course, the very first thing we check, we would find it didn't work. And then we'd say, okay, let's shift it over 1 more by 1, A, B, B, A. Well, you can see we're quickly going to fail on quite a few of these without getting there. The idea of KMP, the philosophy behind it is, if I know that I have matched, in this case, I've matched the first 5 letters, and it's only the 6th letter that things are wrong, does that let me start my comparison now at a better location? Okay, so for instance, if this is failing at this point, I know I might be able to say, okay, I can start my new S comparison 3 back, because I know that I started out with A, B, B, A, and I know that my last letters here have been B, A. The letters just before the one that didn't match were A and B, right? Those were the ones that didn't match. And notice those are the first 2 parts of S. So I know that I have an AB I know that the two most recent letters match the beginning of my string S. And so I would start out comparing A, B, B, putting S down here, A, B, B, A, B, C, D. And I would start checking there. So I already know that these two are going to match. I'm guaranteed that they're going to match because I knew what matched already up here in S. And likewise, if I got to a certain point and something didn't match, so let me give a different example. Let's say that my word S was every, and my word T was let's see, I'll just pick evil. Okay, so every and evil, and again, this goes on for a while. So I matched the E, I matched the V, and now I know, oh, the E and the I don't match. Well, what I know at this point is my previous letter was going to be a V, and there is no way that that matches. So my next point, the next point at which I want to start matching S, will be starting here, E, V, E, R, Y, and I would compare that. Okay, so I know that there wasn't any overlap. In this case, I knew there were two characters of overlap. In this case, I know there wasn't any overlap. And so what that means is I'm not going to start and just shift S over by one. I can actually shift S over all the way here to the point at which I did not match last time. Okay, and the result of this is that after your pre-processing, so you have to pre-process S, but basically after that pre-processing, you're going to have something that's going to run in linear time, order n in the text, rather than order nm in the worst case. Okay, and that's a significant improvement, especially when you have a limited range of things. So let's talk a little bit about how you can actually pre-process this and how these how the algorithm works along the way. So what we are going to do is for a string S length m, we will form an array, and I'll just call the array B. It will be of length m plus 1, so it will be slightly longer than S. It will be, in fact, one character longer than S. Okay, B of length m minus 1. And what B will give us, B will tell us how many characters from the front of S already match if we don't have a match on that character. So basically, this is going to tell us, in this example over here, where should we start our next S? Okay, so in this case, for instance, in this one right here, the answer would have been 2. Okay, because we already knew that two things matched. In this case down here, the answer would have been 0, because we knew that 0 characters matched if the E and the I in this case did not match up. And here, because that B and C didn't match up, we knew that we did in fact have the first two characters would match. Okay. So B is going to tell us that length, and then we're going to use that in the end. So once we've computed B, we're going to use that to pre-process everything longer. So to form B, we'll follow a process, and I'm going to outline it quickly here. If you want to see some details, you can look up the code in the book as well. But the idea here is that to form B, we will, we will keep track of two indices. It will be I and J, and we will initialize. We'll set I equal to 0 and J equal to -1. Okay, and our approach is going to be, our approach in all of this is we will basically see we're going to sort of keep incrementing I and j every step along the way. So I and j will always get incremented, and occasionally j is going to get set back. Okay, so basically, if s of I is equal to s of j, then we will just increment I and j and set b of I equal to j. Okay, otherwise, we will repeatedly set j equal to b of j until either j is equal to -1 or s of I is equal to s of j. Okay, so we're going to basically keep doing this, and then we will again increment I and j and set b of I equal to j. Okay, so let's go through. I'll run through an example of this so that you can see how this works. So I'm going to pick a word that has some nice properties to it, and it's actually harder than you would think to find a word like this. Again, the big advantage of this tends to come up in things like DNA sequencing more than standard English text. So I will pick the word amalgamate. Okay, so this is going to be our word. B is going to be here, so I will draw a box here. Okay, remember B is one longer than the original A. Okay, we will keep track of our two indices, I that we initialize to 0 and j that we initialize to -1. We will also go ahead and set b of 0 to b -1. And just to make it easier, I will label all of these so that we can refer to the numbers easily. Refer to the indices easily. Okay, and so what we're going to do is we're going to repeatedly follow the process that we had before. So we're going to check and see whether s of I and j are equal to each other or not. In this case, j is -1, so there is no s of -1. So what we do is we increment I and j. We make each one go up by 1, and we assign b of I equal to j, so that becomes 0. Okay. We then will do, we will check the same thing again. So we will say, does s of 1 equal s of 0? So a and m are not equal to each other. So we are going to keep moving j back to b sub j. So b of 0 is -1, and now j has hit -1. So remember what we wrote up here. The basic idea is we're going to keep moving j back until it either hits -1 or it reaches a point where si and sj are equal to each other. Okay, so we did that. Now we increment I and j, and we set the value. So it goes to 2, 0. So we set a 0 there. Okay, so now we check and we say, is s of 2 equal to s of 0? Well, yes, s of 2 and s of 0, both s of 2 and s of 0 are a. So those are equal to each other. So we are going to just increment I and j and set them equal. So this will become 3 and 1. So b of 3 gets the value 1. Okay, now we'll say, does s of 3 equal s of 1? L and m do not equal each other. So we will set b equal to b of, we'll set j equal to b of j. So b of 1 is 0. And is s of 3 equal to s of 0? No, L and A are not equal to each other. So we again go to b of 0. It goes to -1. Now we have to stop. Okay, so we're done there. We again increment. So 4, 0. And we put in a 0 here. Okay, going forward, is s of 4 equal to s of 0? No, this will go back to -1. We will increment and we will set that to 0. Okay, now we check and we say, is S of 5 equal to S of 0? It is. They are both A's. Great. So we will increment each of them, 6 and 1, and we will write a 1 there. Now we'll check, is S of 6 equal to S of 1? M is equal to M. Yes, they are. So we just increment each one, 7 and 2, and assign. Okay, is S of 2 equal to S of 7? S of 2 equal to S of 7. Yes, again, they are both A's. And so we'll increment each of them. So it becomes 8 and 3. And we will assign B of 8 is equal to 3. Now we will check and we will say, okay, is S of 8 equal to S of 3? So is T equal to L? No, that's not the case. So J will go to B of J. So B of 3 is 1. So we replace this with 1, and now we check. Is S of 8 equal to S of 1? So is T equal to M? No, it's not. So we change 1 to B of 1. B of 1 is 0. So it becomes 0. We say, is T equal to, in this case, A? T and A are not equal. So this goes all the way back to -1, and now we have to stop. So now we increment. We go to 9 and 0, and that becomes a 0. And finally, we're going to fill in the last one. We check and say, does S of 9 equal S of 0? No, E and A are not equal to each other. So this means that, that would go to -1, which then gets incremented to 0, and our last element is 0. Okay, so that is our pre-processing. This is the array B. And if we look at this, if you examine this, and pause the video for a minute if you need to, but if you look at this, the number that's in here tells you how many previous letters match the beginning of the word. So for instance, if I am here in T, and T is something that does not match. So basically I've got some word that matches all the way up to that T, okay, in amalgamate. Well, I know that what I can do is I can start checking 3 before that. I can keep the first 3. So A, M, A still match. And then it's the next one is where I would need to start checking. Okay, so this is telling me, hey, I've already got something that matches all the way to that point. So I will use an example then and show you how we can use this in just a second. But take a minute and make sure you understand what those numbers are representing all along the way. So we're going to take this word and we're going to see how we could use the pre-processed B array to actually find this word in a bit of text. So first of all, let me kind of just rewrite everything. So we have a amalgamate, and the B values were -1, 0, 0, 1, 0, 1, 0, and 0. Okay, so all right, so there's our word. This is the word that we computed and the B value that goes with it. And now let's say that we have a piece of text, and I'm just going to use this weird one just to illustrate. So we have the piece of text A, M, C, A, M, A, L. Okay, so we have some long piece of text like that, and we want to find whether the word amalgamate is in there. So what we will do is we will start out by taking it, and we start at the very first letter and kind of line it up. And so we check if A, M, A, L, G. We just start checking letter by letter. So 0 checks, space 1 checks, space 2 does not check. And so what this means is, since this one does not work, what we want to do is we want to go to the corresponding, since this is not a match, we want to go to the corresponding part in B and go to index 0 for our next attempt to match. So the next place that we would start then is right here. Okay, now, okay. Notice that what we did not have to do was just move forward one. Because we knew that we'd already matched two and it was this third one that didn't match, we know that not only does it not match if we line it up in the first position right here, we also know that it doesn't work if we line it up in the second position. We don't know yet whether or not it works lining it up in the third position. All we know is that this thing here did not match what we had before. Okay, so it turns out, of course, that A and C do not line up there, so we move it over one more. Okay, and I'll use green here. So if we look here, 0 lines up, 1 lines up, 2 lines up, 3 lines up, 4 lines up, 5 lines up, 6 lines up, 7 lines up. Oh no, 8 does not line up. Okay, so there is not a match there in 8. And so if we look here at number 8, at entry 8 in B, B sub 8 is 3. So since it's that one that does not line up, we want to actually line up the third element. So that's this one right here. That's the one that we want to line up and start checking from. So our next check then is going to be A, M, A, L. Okay, so I'll check these. So now we already know that these lined up. We don't even have to check them again. We will just check this, and what do you know? The L lines up. G, A, M, A, T, E. In fact, we've lined everything up. So we found one location where this occurred. That was that one right there. And now we look and we say, what's the next thing that we need to check after that, after we've gone off the end? Well, now we want to go back to 0. And so that means that the next position that we can start checking at is right here. So we will check the A versus that D. And again, we will see that that doesn't match, and we'll move over and we'll check AMAL and so on, and check one at a time until we start getting some matches again. Okay, so hopefully that illustrates how we can use this B array in order to speed up our operations. So notice what happened right here at the beginning is we matched 2 characters, and then when we had the third one that didn't match, we were able to start by matching by skipping over those first 2 and just checking directly against the third. Okay, and then as soon as we didn't have one, in that case, since the first letter didn't match, we just slided over 1 and checked the first letter. Here we had a whole bunch that matched. It wasn't until we got all the way out to the 9th position to index 8 that we had something that didn't match. And when we got there, we found that because that was the point at which there was something that didn't match, this T and this L did not match each other, we could instead start by just shifting over to index 3 being the one we compare. So index 0, 1, 2, 3 is the L, and in fact the L's matched, and we found a match the entire way. And then again, once we were done with that, we know that, hey, we just had an entire match, so we can go back, and the next thing that we want to match in the space that comes after the word that we care about was 0, so we are going to start matching at A. Notice that if we had something where the word ended in something like AMALG, AMATA or something, this final, if this last E was instead an A, then this value here would be a 1 because we would know, oh, we've already matched one letter there. Even though we found the entire word, we might have matched the very first letter in another occurrence of the word after that. Okay, so that is the KMP algorithm. Again, you see its real benefit when you are dealing with a very limited set of characters that can form your string. That's when it really shines. But that's actually a really important application because that's what's used for a lot of these gene analysis or DNA analysis sequencing type operations.